Ruslan Rajali from JMG, who is the Deputy Director, Geoscience of JMG Sarawak, and Mr. Roslan graduated from University of Malaya in 1988 in Applied Geology and graduated with the Master of Science in Environmental Hydrology from Cardiff University, UK. Mr. Roslan will be giving a talk about deep well construction, hydrogeological conceptual model, and peat management to combat and prevent peat fires at Kolabara MIRI, Sarawak. With that, we would like to invite Mr. Roslan to give his presentation. Thank you.
Mr. Roslan, we could not hear your voice. Actually, you are in already. Mr. Roslan, you are in already. It's just that the voice is not coming out. You can click on this button mute dekat bawah tu. Button di bawah sekali mute ada arrow, Click arrow tu. Okay. Okay, your video is on. Cuma voice tak masuk lagi, audio tak ada. Boleh klik dekat bahagian mute dekat bawah tu. Yeah, and check for the mic.
Roslan, can you hear us? We cannot hear you.
Hello? Hello?
Okay.
Can you hear me?
Yes, yes.
Okay, okay. Okay, can you hear me?
Proceed, Roslan.
Okay,
Okay.
can you hear me?
Yes.
Okay, okay. Okay. Okay, I'll start again. Okay. So, thank you, Mr. Chairman, Judge Jones, and very good afternoon to everybody, distinguished speakers, and to all my colleagues. So my topics of my presentation is on tube well constructions, hydrological conceptual models, and peat management to combat and prevent peat fires at Kuala Baram, MIRI, Sarawak. So the outline of my presentations, I will touch on the objective, regional geology, geophysical survey, hydrogeology, peat management, outcome, and finally will be the conclusion. This is the map of our study area. So the study area is located at MIRI area at the top northeast of Sarawak. So the objective of this investigation is to locate and develop groundwater as a source of water supply to combat and prevent peat fire and smoldering. Peat fire and peat smoldering. So what we're going to do is we identify the big potential, high potential of soft water supplies, and for this we're going to abstract it to prevent this peat fire. This part of the study area, which is including surrounding sekolah jenis kebangsaan Chunghwa Tudang and MIRI. The regional geology of the study area is covered by quaternary deposits, and then it will be underlined by liang formations, and followed by interfingerings of MIRI formation and Tukau formation, and underneath it is a Lambe formation, and deep down below is the Sibuti formation. So this geology maps the sources from this LIDAR 1960, and also MIRI geology in block diagram source MIRI water supply master plan study 1990. What we did is, what we do for this desktop study was the slide that I mentioned before this. From this desktop study, the geology of the areas, from this geology of the area, then will be followed by geophysical survey. So what we did is we identify based on the desktop study or geology of the area to locate certain area to do geophysical study. We use 2D resistivity vertical imaging methods. This is our inversion model analysis. And from this 2D resistivity study, we try to locate groundwater potential area and also estimates the lithology down below. So during this resistivity study, there will be some interference which is being influenced by gas pockets, fresh water and salt water. So we have to take this into account during our interpretations of the 2D resistivity study. So what I mentioned before this, we have this geology study, and we also have this desktop borehole and field observation to be relate with the geophysical study to come up with a potential groundwater area. For this geophysical survey study, we set sand body which has a value of 30 to 200 ohms, and for the clay layer, 5 to 20 ohms. To bear in mind, for this Kuala Baram area, the area that we go for this geophysical study is the quaternary deposits, which is of a very thick layer of alluvium quaternary that could reach up to 200 to 300 meters. So this is the profile of geophysical study of the area. We have been selected based on our previous desktop study and borehole data and other data. We are using 8 meter spread of gradient protocol. So from these slides, the arrow represents where is the location of the profiles of the geophysical study. And for each profile, we try to interpret where is the layer of peat, where is the layer of sand, where is the layer of clay, and the big sand body. From this 4 profile, the top layer, so mostly there we can identify the peat layer, and then it will be followed up by a sand layer, thin sand layer, and then underneath this thin sand layer is the clay layer before we reach this sand body. So from this profile, we're going to go target the big sand body down below. From this geophysical study is at a range of 40 to 70, 80 meters depth. Must bear in mind, this geophysical study, even though at the peat area is just very thin layer. So we didn't try to look for groundwater source at peat area. We are going for big aquifer at sand body area. And from this geophysical study, we can interpret the sand body, most of the area is of lateral continuity. Lateral continuity means the sand body, most of the area is connected to each other, but there's a big sand body and there will be some area with a pin sand swell and then a big sand body. So we're going to target the big sand layer to extract, to locate for this groundwater potential. So this is the data that we get from Link, which has carried out 87 hand auger drilling with a total depth of 415.6 meters. He has been studied this area on pits in 1995. From the thickness, from all the data that I collect for this link, which is of 87 drilling data, we come up with a conclusion: the area, the pit thickness is not that deep, and then it's not also that shallow. It's around 1 to 5 meters. This pit is of characteristic of homogeneous and topogeneous, and it is of a raised bog type. Edison 1964. From this link data of 87 auger drilling, so we come up with an isopath map of pits. We generate this isopath map of pit. This is the isopath map of pit of Kuala Baram area. The peat, the high thickness of peat on the east is the thickness is much higher compared to the west. The peat at the east is around 5 meters and less, and on the west is 2 meters and above. And you can see the legend down below, the color of the pits, which is the highest one will be the blue, which is 5 meters, followed up by the green, which is 4 meters. And the lowest thickness is the light green blue, it's 1 meter. The site geology of Kuala Baram area. We have to look at the site geology. It's very important to identify the site geology of the area, other than the regional geology. Just now I mentioned about the regional geology. Now I go for the site geology. We need to know the site geology of the area to zoom, which of all the potential area with to zoom to maximize, to identify which area have a good aquifer. So underlying peat is a very fine grained dirty sand layer, thickness 7 to 11 meters. So this sand layer, even though it's a good aquifer, but it's of a dirty sand, from this it can imply that the groundwater potential is a bit less. Then it will be followed by a thick clay layer of 28 to 48 meters. And then underlines this thick clay layer is the fine to medium grain clean sand of thickness 21 to 58 meters. And this is the target aquifer layer of good clean sand of fine to medium grain. So this is a source of water supplies that we're going to look for to settle the problem of this peat fire as a source of the water supply. And below this fine to medium grain clean sand layer, we have this clay and schist clay layer. During the drillings, construction, we have 10 tube wells been constructed at Kuala Baram area. One tube well is we use water jetting methods. It's more on manpower ways of drillings. The wells can reach up to 11 meters. So we have one tube well of this. So this tube well, of all the dirty sand layer that we identify, even though it's of a low to medium potential, but part of it, more or less like certain patches, they have a good clean sand layer. So that's the place that we construct this tube well. And then we have a very deep drilling well construction, which we want to hit the deep aquifer, the one that have the high groundwater potential. We have 9 tube wells. We are using rotary drilling, mud rotary drilling. So depth is in the range of 33 to 111 meters. So we managed to have a good discharge of the tube well at this area. The range is from 4.5 to 90 meter cube per hour. This want to show a bit of pictures of drilling a well constructions. Tube well KB16. KB16 is, if those of you have been to Kuala Baram, to MIRI, if you happens to be there, and there's one Menara Tinjau. They call this the way the place that they monitor for this peat fire. The place, there's one well been located there, is KB16. We constructed at that area. And from that picture, you notice the brownish part is this is a homogeneous peat. Homogeneous peat is type of peat that prone to peat fire compared to homogeneous. So KB19, the site for the other photo is this way is located near to Curtin University. So have a very good discharge of 90 meter cube per hour. This is, I want to show you a bit of fence diagrams whereby we interpret house down below to 3D based on all the 10 wells that we constructed. Based on the lithology that you have, we come up with fence diagram. So from this fence diagram, you notice the brownish part at the top is the PEAT layer. And then come up with the yellow one. That one is mostly of this fine grain dirty sand, around near up to 11 meters. And then there's a blue layer. After this sand layer, this yellow one is a clay layer. And then the middle part is the thick sand layer, the yellow, the middle part is the thick sand layer. So this thick sand layer, this is the groundwater potential that we are looking for. This the area have a low good potential. So in the middle, you can notice that I did mention top sand aquifer, top 11 meters, which is of low to moderate groundwater potential. So the big sand layer down below, I consider is as a low sand aquifer, thickness 21 to 58 meters, high groundwater potential. So for me to confirm most of the area have a lateral continuity, what I did, I tried to interpret, analyze geophysics, the fence diagram, and also the pumping test. Pumping test is very, very important to know the characteristics of the aquifer. This is the pumping test that been carried out, and so the areas where the pumping tests have been carried out, the top ones is the well-constructed tapping top sand aquifer, tube well KB5, unconfined type. This is the one that I mentioned, one water jetting that been carried out just now using the manpower. So this is going for this dirty sand aquifer, the top sand aquifer. So from here, so it's of unconfined type, whereby you notice from this pumping test data, it shows that there's no boundary or disjointed cases for the top sand aquifer. The other two graph is for the lower sand aquifer. So top sand aquifer, it shows there's a slide, there's a bit of, showing no lateral continuity of the sand layer. And the other two graph, the other one is on KB16 and KB19. It shows the pumping test at confined type. KB16 is of a confined type, KB19 of a leaky type or semi-confined type. From this, you notice the pumping test, the drawdown is slowly going down. Doesn't show some drastic movement of drawdown as compared to the top sand layer, the first graph. The first graph, you notice that abrupt drawdown of the water level. So it shows there's no boundary. But the second graph for the KB16 shows, even though there's a drawdown, but it's going down smoothly. Smoothly going down, there's no recharge, no sign of recharge. From here, you know, the low sand area of this particular area is of confined type. For KB19, it's also tapping the lower sand aquifer. And you notice that while they're doing the pumping test, it shows a gradual drawdown of the well. And then there's a there are symbol sign at the end, nearly to the end of this, during this duration time of pumping test, showing encounter source of recharge. So when there's showing source of recharge, so we assume there's a leaky somewhere, connection somewhere, probably from down below, probably from the formation down below, which is of a liang formation, could be from the tops. So this there's a flow, could be a vertical flow, could be of a lateral flow, which filling up this area. So when this sign of recharge, so this area we consider is a not of confined type, of semi-confined or leaky aquifer. Leaky because there's some connections somewhere at the layer that filling up this layer. And then from this graph, for the lower cell layer, even though it's of confined type and leaky type, from this graph, we can interpret the sand layer almost continuous at that area. So it's not sand which is isolated. Sand isolated will not show this way. Sand isolated, this means the aquifer is only at that certain place. But this one is connected. This means that it shows that some recharge somewhere filling up the aquifer at this area. So sorry, there's a bit of technical. Okay. So this is the water quality of the area. So the iron content for the water, the iron content is low to medium, is 1.9 to 13.7 milligram per liter. pH neutral, so very PEAT of alkaline type, PEAT only, 7.2 to 7.8, but the chloride is quite high, medium to quite high. The chloride content is almost, most of the area is almost considered as a seawater, salt water. The chloride is of 520 to 12,426 milligrams per liter. From these Piper diagrams for this water quality, the anion is of chloride types and the cation is of sodium to potassium type. Okay, I would like to touch on the peat management. Process involved in peat management to combat and prevent peat fire and smoldering. So this, as I explained before this, so we need to have a peat management for this area. So from this management, it's normal that we usually, for the geology, we do a geology study, as I mentioned before, geophysical study, and then come up with a hydrological study, all the fence diagram and all the data, the pumping test, everything. Then groundwater resource management. So groundwater resource management is how we're going to tackle the peat area. How we're going to make sure the peat will not be damaged. So what we did, so I will show after this how we go about for this groundwater resource management, which being assisted by infrastructure. Okay, this is the picture of the peat management, the infrastructure, whereby we need mineral tinjau, high-level structure. So for this infrastructure, this has been done by JMG, by Jabatan Alam Sekitar, by JPH, Badan Perairan, and the MCC, MIRI Municipal Council. So construct a high-level structure. This high-level structure, the function is to monitor. So where we employ radar to monitor for any area which we notice there's a peat fire. And from there, they're going to inform us all to prepare for this pumping out water. So for this, from this mineral tinjau high-level structure, whereby we monitor area where there's peat, and we also monitor for a drop in water level in the drain. During dry season, we're going to monitor closely the drain at the peat area to make sure that the water level is high enough because if the water level in the drain is quite low, then the pit at the top will be dry. So these chances for it to burn quickly will be high. So that's why we have construct this high-level structure. And then this high-level tensor has been constructed by the MCCC. We have also the check dam. Hello, Dosia. Dosia, saya dalam presentation. You boleh tadi saya ke saya untuk kata haluan. Okay. Thank you. Sorry, because I have two video conference. I have another one video conference which I have to chair. So now I ask my assistant to assist me on the other video conference. We have one discussion with all the water authority all over West Malaysia regarding our plan, guys, panduan on the tube wells. So a lot of them attend that video conference with us. So you are starting this early morning. Sorry to disturb. So okay, I continue with my presentation. So this Benda Tinjau is being constructed by the MCCC, and then this infrastructure part of it also is a check dam. We need a check dam. Check dam be constructed by the JPS. Check dam. The function of check dams is to prevent water from flowing out from peat fire-prone area. So we have to construct a check dams to prevent this water from going out. And then we also have a fire breaker or a drain. So this fire breaker is a drain. The function of it is first is to fill up the drain with this groundwater. And then from there, and also the function of the fire drain is also to prevent fire of certain area of pit area from migrating to the other area. So this drain will prevent fire from migrating one place to another. Then we have the tube well, submersible pump, and genset. So this is work of JMG, our jabatan. So we construct tube well, as I mentioned before, deep down below up to for this area is 80 meters, and from this 80 meter deep aquifer we construct, and this water will coming up shows the water coming out and fill up the drain, and then will be prevent the pit fire. Okay, this is the area to show where's the fire breaker, and show some maps that we constructed before, and where's the drain from the 3D models I show on the right hand side. Okay, so from all my study, from desktop, geological study, from all the data, previous data, borehole data, geophysical data, and hydrological data, pumping test data, and some taken some data also from Lembaga Sungai for the Batang Baram. And notice down Baram is up to down below. That one is based on what I got data for Lembaga Sungai. It's about the depth of the Kuala Baram at that area, probably around, based on that data, is around 70 meters, plus or minus. Okay, from all the data that I mentioned, I compile, I interpret, I come up with a 3D visualization. I call it hydrological construction model and pit management. I combine into two. Hydrological construction model to visualize in 3D and how it can solve pit fire and also for pit management. So from here, so what we do, we construct. Okay, I repeat again. From here, you can visualize everything how we going doing this pit management. So we have thick aquifer layer, fine to medium grain, sand good aquifer, lower sand aquifer. And then the clay layer at the 60 meters and 4 meters in the peat layer. This model is not to scale. Then you have a fire breaker in the middle. You have a check dam, and you have the batang baram. So now you can assume, visualize, you are at Kuala Baram house, it looks like. So this of layman's style, just when you can understand. So the yellow is, a lot of this patchy yellow is peat fire. And inside the peat, that one, the yellow is inside the peat, inside the brownish peat, that one is the smoldering peat. The problem with peat fire is to tackle smoldering peat. It's very hard to tackle this smoldering peat. This is the one that causes haze, which can cause this transboundary haze that can affect our neighboring country like Brunei and Kalimantan. So the peat fire itself on the surface is easy to tackle, but smoldering peat is very hard to tackle because it's deep down below. If it's much deeper, it's much higher to tackle. You never know. When you are at the site, you never know that the peat there is not burning anymore. Even though at the surface, you as a bomber, people extinguishing this peat, the peat fire. Even though at the surface, peat is totally it's not burning anymore, but it's deep down below, it's still burning. And long time ago, before we have this peat management at this area, when they try to extinguish the peat fire, it's only settled for a few hours, and when come to next day, it come out against burning. You know why? Because the smoldering peat, because the peat down below is still burning, doesn't show. But when a few hours after that, they will come out again and they start to create another fire. So what we did is we tried to tackle this smoldering peat.
Mr. Roslan, can you speed up a bit? Take time.
Okay, so what we did, so we pumped from this aquifer from using a high capacity submersible pump. They can heat up to 100 meter cube per hour, and from this pump we fill up the drain, and with this fire drain or the fire breaker, so this check then blocks the flow of the water. So when it flow the water, when it's full, will be overflow. You overflow the peat area, and then when it overflow the peat area, it will be seeping into the peat. While it's seeping into the peat, then it will be slowly extinguish the smoldering peat. From there, can tackle the smoldering peat from this one. Okay. This so a bit of a visit by my explanation to the VIP that we visit last time. I was there by this our Deputy Chief Minister Yang Muhammad Dato' Ahmad Douglas Uga and Dato' Lim Kim Sing and our former KSU and our other, and then also this from Brunei, this orang kaya yang mulia Pehin orang kaya Menteri Pembangunan Brunei, also try to want to know the technology that been carried out in MIRI, and also previously there's a visit from the Indonesian 40 government delegate from Kalimantan to know our technology, how we tackle this smoldering peat. So I did have some explanation. I did some photo of the area. And then outcome of my presentation is this. From this study, it can result in reduced heads, reduced habit-related health problem, no transboundary heads. And the conclusion, I covered very fast, two types of aquifer, top sand aquifer, lower sand aquifer. And the top sand aquifer is low to moderate groundwater potential, unconfined. Lower sand aquifer, high groundwater potential, confined to the east and leaky to the west, very high discharge rate, up to 90 meter cube per hour, can sustain long hours of pumping under recommended rate, lateral continuity as a source of the supply for peat management to combat and prevent peat fire and smoldering. Okay, okay, that's all, and thank you very much.
We'll open we'll open the session now to the floor. So if there is any question, please get right into our chat room.
And we cannot sustain. And therefore, learning happens. Okay. And I think it is very fair to do that.
I would like to ask for questions from anyone. You can ask the question, or you can go into our chat room to ask. If we don't have any questions, then I think thank you, Mr. Roslan, and we'll go to the next session. The next speaker will be Mr. Edward Moore from JMG. Okay, the next speaker would be Mr. Edward Moore from JMG Sarawak, and Mr. Edward graduated from University Malaya in 1994, and he has a Master of Science in GIS from UNIMAS in 2019, and is currently the head of the engineering activity for JMG Sarawak. Mr. Edward will be talking about generating landslide susceptibility map using airborne LIDAR derived parameters and geological mapping factors for Canada Hill, MIRI, Sarawak. Please, Mr. Edward, welcome, and you may start your session. Thank you. Edward, yeah, you may proceed.
Hello. Hello, good afternoon. Can you hear me now? Hello, good afternoon. Thank you, Mr. Chairman. Okay. Is it okay?
Okay.
Okay, good afternoon. Thank you, Mr. Chairman. So my presentation is entitled Generating Landslide Susceptibility Map Using Airborne LiDAR Derived Parameters and Geological Mapping Patterns for Canada Hill, MIRI. This paper was written together with my supervisor, Prof. Dr. Gabriel Tonga. He's during the time he was the director for the IBEC UNIMAS. So, an overview, okay. Landslide is one of the most damaging hazards on Earth. It's a natural hazard complex. It consists of factors, and with current technology, we have the advanced remote sensing and GIS. We can identify actually high resolution image to identify high risk of geohazards. And in Malaysia itself, since December 1919 until 2015, we have more than 500 life loss with total losses of
Hello, Edward. We are not getting any sound from you. Can you hear me?
How the wind area actually can contribute on such emission.
Hello, Edward.
First question.
Hello, Edward. We are losing signal. Yeah, Edward, are you there?
Yeah, I'm here.
Try again.
Um,
Go ahead.
Go internet connection.
Yeah, we can hear you.
If you disconnect.
Can you hear me?
Yes, we can hear you.
I got problem with the presentation actually.
Okay. You try.
Okay.
You try again. Share again.
Okay.
Share again. Is it?
Maybe can you open Roslan Rajali for me? Because I need to change computer.
You think
Ada internet? Dah tahan.
Ada internet.
Sudah.
Okay, we can see you.
Can see me?
Yes.
Sorry.
Okay.
But I got problem with the presentation. I cannot share the video.
Maybe some contraction here. Actually, I cannot put that.
oh
Especially when it comes to utilities. So, what reserve, for example,
Yeah, try to share the video.
sharing using
Yeah. Hello, Edward.
Hello, Mr. Edward. Are you using under Edward or under Ruslan? No, it's Mr. Ruslan.
Edward, are you there?
I think it's not in.
Okay, Edward. Okay, you can try to share now. Okay, we are. Okay, you can proceed.
Second will be the soil location and accessibility, material and methods, result and discussion, and other components. Okay. Yeah, as you can see, since 1990 was now, we have a total economic loss of more than 3 billions, and with total loss of lives is more than 500. As you can see, this are all the events that have been occurred since then. The Mansa 2008, we have the Helen Towers, we have the Pos Dipang, the debris flow in Pos Dipang, we have the Bukit Lanjan, and about on in Sabah itself, we have the Ruang Cangkul 2002 with fertility of 16%. Another one in Sabah with cost of 9 millions. And this is the one that occurred in MIRI. In 2009, we have the Lereng Bukit landslide, we have the Kulis Pengkuri Bujang landslides, and we have each in Skapit, Bukit Cina, and in Kampung Lanjang, Sinjo, and Sirian. All those landslides we have fatalities. So the main objective of the research is to develop a sustainability map using LIDAR data and GIS technique based on the main objective with the specific objectives such as to generate DTM or digital terrain model and DSM, digital surface model from the point cloud data from LIDAR itself, and to extract the parameters from the TM such as the length, the slope gradient, slope aspects, the rivers, and so on. And based on these parameters, we developed the landslide stability map together with other parameters such as the vegetation cover, land use, and geology. And lastly, we validated the landslide stability map based on the randomly selected landslide data. Okay, this is the literature review. They've been gone through the LIDAR, what the slide image, what area photographs, the GIS, and what type of landslide. We have few type of landslide, which include topples, faults, landslide, and with different materials, either coarse materials, debris, or earth. This is the type of landslide with some of the terminology of landslides. Okay, the location of the study area is Kennedy Hill MIRI. It's situated at the northeast part of Sarawak, in MIRI itself. And my study area, as you can see, is the the Bukit Canada itself. Location and stability, we have the northeast trending hills above coastal alluvial of the MIRI city, with drainage of subparallel and treeless. All these are controlled by the geological structures in Bukit Canada, such as the faults and the bedding. And we have land use of forest and low vegetation in Bukit Canada, and 1/3 of the area is covered by vegetation of 5 meters. So this is the material method. The frequency ratio is one of the method that we use to detect how to see the probability of landslide occurrence to non-landslide occurrence for given tribute. So from this frequency ratio, we will see the number of pixels they containing in each slides compared to total number of pixels. We are study based on the pixel of the in the GIS. Okay. So we are using the software such as the GSA software, the ArcGIS with the extension of 3D analysis and spatial analysis, just to process all the data. Mostly we are dealing with the point cloud data. And then we're using the global mapper to study or to analyze the biomass, and also to analyze the satellite image and to extract some of the geological features. So as I mentioned now, this is LIDAR, and what LIDAR is the one of the scanner that we are using this LIDAR can be considered two parts. Either it's airborne data LIDAR or the terrestrial LIDAR data. But what we're using now is the airborne LIDAR data, where there's a range of light that have been emitted from the instruments, and will pass this pulse will direct to the ground with first return, second return, third return, last return. Whether we're considering the last return so that we can do what we call the digital terrain model. This is the example of the airborne LIDAR data. What you see, the image, actually is the point cloud they've been intensified with a certain intensity. You can see it's a point cloud data itself. The data we're using is with density of 2 to 3 points per meter cube. So from this LIDAR data, we will generate the digital terrain model, where we can find generate the hillshed, and also we can abstract fault, valleys, and landslide, and also some other parameters such as the slope gradient, slope aspects, and some other parameters. So this LIDAR data that being abstract just for the Canada Hill. Actually, the LIDAR data include the whole area, but I just abstract the one in the Canada Hill itself because it's the hilly area, because this is the area they want to study. And later on I'm using the LIDAR ground data last data set, LIDAR data set to have the last point elevations. Then lastly, this is the hillside azimuth of 135 degrees. Okay, so to extract the landslide, I'm using the certain azimuth of the hillside based on the hillside of 45 degrees, 90 degrees, 135, 180, 225, 270, or 135. From that azimuth, you can see the landslide, and from that also, I'm using this method just to lineate the slide before going to the field, just to counter check the landslide itself. So this is the elementary that we're using, and this is the landslide, one of the landslide that been detected. Is one of the landslide that occurred in 2000. and 1995. That has been covered by vegetation. But from the landslide, from the LIDAR data, from the hillshed, actually we can delineate it from the hillshed. Okay. This one, the satellite image that we use is a spot 5 image with cell size of 0.5 meter. And beside the data acquisition, we are also doing fieldwork. So most of the fieldwork we're doing is for geological mapping to see what type of rocks, what type of formations, and landslide inventory also to counter check what are the landslides that have been detected in the hillshed of the LIDAR data. And then we're also doing mapping on the biomass to see the diameter of the trees and to delineate what's the biomass of that area based on the tree height, the canopy itself. This is the geological setting of the area. Regional geology is consists of the MIRI formation in the top northeast area, mostly in the Neogene. And this is the site geology. We can see the thick and intercalated interbedded of shale and sandstones. And you can see you have alluvial. Actually, what we see the yellow color, the MIRI formations, it consists of interbedded massive sandstone and massive sandstone, also the interbedded of shale and sandstone. And the Tuka formation is mostly interfering with the MIRI, but it's more to the argillaceous type. West terrace deposit is sit on the MIRI formations. It consists of the sand layer. Okay, and this is all the structural geology that you can see in the area. We have the normal faults, and those are the cross section of the fault. They've been encountered from the shells, and also the cross section of east to western side of the area where the anticline of MIRI. Okay. And this is the biomass mapping that we did because my supervisor is forestry, and he wants us to what is the connection of the biomass with the landslides. So this is the plot that we did on the biomass mapping. We have around 15 plots. Okay, and from the landslide, we have around 35 landslides that have been identified either by land hills detect from the hillshed and counter check on the field. We have 35 landslides altogether. So this is the parameters that have been chosen to the causative DTM parameters that have been chosen to which act as the causal factor for the landslide. So from the DTM itself, I abstract landslide also, as I mentioned now, the slope gradient, the slope aspect, the curvature, the LS factor, linear density, and distance, drainage, and topographic wetness. Whereas from landslide, from fieldwork, we identified the landslide, as mentioned now, to contextualize the landslide, the lithology, the geology or lithology, the biomass, and from satellite also, I detect the biomass, analyze the biomass from satellite image, also the land use. Okay, so this is the causal factor. 11 causal factor have been chosen for to generate the landslide stability map. There's the slope gradient, slope aspect, curvature, LS factor, lithology, linear density, soil, distance to drainage, topographic wetness index, land use, and biomass. So this is the causal factors derived. The map, the linear density, the aspects, the curvature, topographic wetness. This derived from LIDAR data just now, distance to drainage, and LS factor. Whereas the one that derived from satellite image and fieldwork is the lithology, the soil series, and the biomass, and also the land use. So this is a conceptual framework for the studies, which include the data collections, either from previous study, raw data LIDAR, where generate the TM, and generate also some of the causal vectors, and also from geological mapping, the satellite image. Okay, so I'll select few landslide for the training and for the validations. And from the training, I produce the probability of the frequency ratio. Before I produce the susceptibility map, and then from the landslide susceptibility map, I will do landslide validations to produce the final landslide susceptibility map. Okay, this is the flow chart. The landslide inventory, the input data, the landslide training with the cross section with the vector maps, and then the frequency ratio map, and final is the landslide stability map. Okay, result discussion. The probabilistic approach to correlation between landslide and causative vectors. So you're using the frequency ratio to see the spatial relationship between landslide location and each landslide related vectors. So as far as taking as one as an average value, if we see more than one, we have the higher correlation. So from that, we can see which are the factors that contribute most or that cause the landslide. So this is the frequency ratio variables. As you can see, if we see more than one, we have higher correlations. So this is the aspect, the curvature. You can see the northwest, and also the curvature, not much delay. And then we have the slope. Which slope is it? Normally, if we see if the slope is more than 60 to 90, it can cause landslide, but it's different here, where we can see the range is from 25 to 60 degrees. We have the LS vector, the lineament. Lineament is the density of linear. More density is much higher. The frequency ratio variables. And also, if you can see the distance to drainage, not much actually. And then, if you can see the lithology, is mostly intermediate sandstone and shale actually. And then the soil is on the MIRI series. Land use, if you can see, most of it with higher vegetation. Maybe I can explain later. And also the biomass. Biomass is, you can see, is 16 to 51 kilogram per hectare actually. We count the biomass by kilogram per hectare. Okay. And then this is the frequency ratio map for each slope. This is for the slope and have the curvature. Frequency ratio for the curvature, the LSI factor, the aspects, the lineament density, wetness, distance to drainage, lithology, soils, land use, biomass, and this is how we calculate the landslide stability index or the landslide stability map. So we use the LSI formula. We total up all together the frequency ratio to produce the landslide stability map. So this is the map. Landslide stability index with very low susceptible, low susceptible, medium susceptible in yellow, and very high susceptible in the red area, mostly in the northeast of the Canada Hill. So for validation, we're seeing the ROC curve. We have landslide. As mentioned now, we have training 74% of landslide of 25, and then validation 20% of the landslide that have been collected. So the area under curve is around 96% actually, lower bound, and 98% upper bound. And so it's around 97% actually. And then I consider also using the reclassified value, mostly in the area of high to very high, with around 89% or 90% of area are covered with landslide in the very high area using the validation index. Okay, as mentioned now, it's randomly assigned the landslide that been selected for the validation, and the training is randomly assigned. It's not being selected manually. So for the ROC, reservoir operating characteristic and area under curve, we have 97% as area under curve is the stability map is most the landslides under the high substrate values, class high to high, very high. So landslide variation in LSM also is medium to very high stability class. So nearly 99. Actually, if you consider the medium is 99%, but if you consider high to very high, it's around 90%. Okay. So discussion, as we can see, topographic factors is one of the factors that affecting the landslide. As we can see, most of the aspect is facing to the west or northwest, and also the curvature, and slope is bedding is 15%. Which one is more than 50%? As mentioned now is 35 to 60 degrees, but you can see bedding is 20 to 25%. Actually, most of the landslide that occur in MIRI itself is translational landslide. It's daylighting because the bedding is dipping to the northwest, so also the slope facing. And the geological factor is lithology is interbedded sandstone and shells, which show the frequency ratio is 7.26. And MIRI and Tatao series is consists of fine sand and sandy loam, which polydrain with frequency ratio is more than 1. This is also one of the factors that affected that contribute to the high index of land stability. Lineament also, it high density shows high frequency ratio. And runoff also triggering factors for landslide, because most of the area is a fault plane, and the stream is follow the fault plane. Hydrologic factors such as distance drainage not much actually contribute to the landslide. And the anthropogenic factors influence human being and nature. The land use, if we can see, barren is contribute 1.12, whereas high vegetation is 1.6. Okay, barren is area of landslide at the moment, but the relic landslide is of high vegetation because the most of the relic landslide there's an overgrowth. There's overgrowth. That's why most of the for the layers we have the high vegetation that contribute to the area with high vegetation that contribute to the landslide. And also for the biomass, where there is area of 16.40 kilogram per hectare. This means to say those area with high vegetation of 86.92 kilogram per hectare does not contribute. We have the less than 1 frequency ratio. So,
Edward, time is running out. Maybe you can speed up.
this is the main better the controlling the spiritual slide and study area. We have the, as we can mention now, is the topographic factors is considered the geology contribute 44.4%. And the topographic factors we include the slope aspect and the slope gradients. And the geological factors contribute 31.9%, and hydrologic and anthropogenic factors contribute 23.6%. So, but if we trim down to the factors itself, the intermediate of shell sandstone is which frequency ratio of 7.26, and the LS factor of class 5, and the soil limit density. This is the one that contribute most of the control the stability of the study area. Okay. Conclusion. So 11 factors generated generated from the TM LIDAR data, satellite image and fieldwork. And the delineation of topographic vectors is also appropriate is closely related to geological structures. And the anthropogenetic factors, that's in the biomass, is not affected the stability of the slopes. And geological factors of lithology and the luminosity is the major factors and not the vegetation cover. Okay. And the other one is the quantitative method probability frequency ratio was used. It is simple for high resolution data which predict the slope failure on a cell by cell basis. And this result of saw 90% of the relation data fall within the high values of susceptibility. This means high to very high values of susceptibility. Okay. So this shows that the LSM developed from parameters extracted from LIDAR data can be used by decision makers and use planners and to avoid the landslide susceptible regions. Okay. So study proved that geological factor act as the main constitutive factors that affected the stability of slopes. Okay. And okay, I think this is the conclusions of four factors: topographic, geologic, hydrologic, and stability factors. So probabilistic frequency ratio is used for landslide stability mapping. It's not mentioned 35 landslide, DTM sector, slide imagery, and field data. 30% were used for landslide data for training and 26 for validation. So this is the constitutive factors: slope aspect, curvature, LS vector, lineament, the lithology, soil distance to net, total wetness index, land use, and biomass. Okay, AUC plot is mentioned 91.1%, and susceptibility of zone high and very high is 90%. Okay, so that's all. Thank you.
Okay, thank you, Mr. Edward. There are a few questions actually, which from the floor. So one of them is, can you explain how the category high, low, medium of the landslide map is divided?
Oh, the high and low is based on the equal value in the landslide in the it based when we use the GIS is on the equal value. So every value is the same. In the GIS, we actually the high.
Oh, so okay, it is based on the you extract it from the GIS.
Yes, GIS automatically using the equal value.
Yeah. Okay. So another question being asked is, can the model be used to predict landslide?
Yes, because we know what are the factors that cause the landslide. Can predict based on the factors that will be identified. Which one the most frequency ratio? So for MIRI itself, we know that the intermediate of sandstone, also the faults that cause the landslide in the area.
Let's see. Okay. So one more question is, probably in this study, what is your opinion if you want to combine the aspect of seismic microzonation to be included in this framework?
Yeah, because that's why I mentioned that if we can, because we are at this moment in study until the landslide stability map, we haven't include what is the triggering factors that can trigger the landslide. There are few triggering factors that we can identify, either is rainfall or seismic. So these are the two factors. If we can include in the study to produce the hazard map.
So okay, so I think that's all. I think we don't have any more questions from the chat room. So thank you, Mr. Edward, for your presentation and for your time. Okay, so okay, so we go to the next speaker. So we'll go to the next speaker, who is Mr. Muhammad Farid bin Abdul Kader, who is attached to the Technical Services Division of JMG in Ipoh, Perak. Mr. Farid, Muhammad Farid, has a BSc degree from the University Kebangsaan Malaysia in 2009, and recently he had a master's disaster risk management from UTM in 2019. He joined the department in 2012, and Mr. Muhammad Farid will be talking about debris flow study of Sungai Mandi, Santubong, and Kuching Division, Sarawak. So welcome, Mr. Muhammad Farid, and you may proceed with the presentation.
Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon. Thank you so much, Mr. Jaitish, for the kind introductory. So let me share my screen. Okay, so today I will share with you the topic of debris flow study of Sungai Mandi Santubong, Kuching Division, Sarawak. So this paper was written by me, myself, Mr. Edward, Mr. Clarence, and also Mr. Fidaus bin Razman. Okay, this is the content of my presentation. We look briefly on the introduction of the study area. Then we go for material and methodology. After that, we will go through the results, also discussion, followed by the recommendation, and the final one is the conclusion. So as the Mount Santubong, maybe everybody knows, it's one of the landmark of Santubong National Park that was located 35 kilometers to the north of Kuching, and it has various type of environment in Santubong, like rainforest, the mangrove forest, rivers, nearshore waters, and also the mudflats, and it has a variety of wildlife. And this area is one of the tourist hotspots in Kuching. And there is some interesting locations that are located in Santubong, such as the village and also the Damai Beach Resort. Okay, this is the main topic of my presentation, which is the debris flow event. This debris flow event was occurred in 2015 and located along of Sungai Mandi, one of the main river in Santubong. And fortunately, there is no fatalities or injuries recorded during that time. But it caused damage to properties. Some of the roads have been damaged when it's struck by the debris flow. The objective of this study, the first one is to identify the geological factors that contribute to the debris flow event. And the second one is to recommend some relevant preventive measures to minimize the risk of debris flow in Sungai Mandi area. So this is the location of the study area. I will just focus on the west part of this Mount Santubong. You can see at the screen, the red one is the debris flow route that represent the Sungai Mandi. At the downstream area, there is human activities and also some infrastructure. There is Damai Central and also Damai Beach Resort at the end of the river. So in terms of topography, most of the Santubong area is made up of hilly and undulating terrain. You can see from the maps, the highest peak of Mount Santubong is at 840 meters from above mean sea level, and at both flank of the Mount Santubong, the elevation range from 20 meter to 300 meter above sea level, and in terms of the slope gradient, the both flank of the Mount Santubong range from 5 to 25 degrees, and at the center of the Mount Santubong, the slope gradient change abruptly, more than 60 to 90 degree. And in terms of the drainage pattern, there is three major river in the study area, which are Sungai Penyok, Sungai Tambak, and Sungai Mandi itself. And the pattern, we can see that it shows a sub-parallel to parallel drainage pattern and are joint control. And the river are generally swift and straight with a few tributaries, and all flow in the same direction to the west of the study area. And in the Sungai Mandi, we can find a big catchment area that flows water into Sungai Mandi. And based on this data, approximately the total area of the catchment area is approximately about 1 square kilometers. So if compared to other catchment area in Mount Santubong, this is considered relatively big. In terms of the geological setting, I just focus on these two main lithology of Mount Santubong. The first one is the Padawan formation that consists of intercalation of shale, fine to medium grain sandstone, and also the subordinate sandstone. And it is generally steeply dipping. And another type of lithology is Kayan sandstone. This is most lithology, type of lithology in Mount Santubong that consists of thickly bedded sandstone with subordinate shale. And at the southern part of Mount Santubong also, you can find the angular unconformity between the Kayan sandstone and also the Padawan formation. The Kayan sandstone is at the upper boundary, and the Padawan formation is at the lower boundary. And for the site geology, we can find some of rock outcrop if we go along the Sungai Mandi area, and most of the study area is consists of Kayan sandstone. And when we go from the bottom part of the Sungai Mandi up to the upper part, we can see the changes of rocks in terms of weathering grade. At the bottom part, the lower part of the stream are thick bedded to massive with weathering state of grade 3 to 4. and also we can find the interbedded with subordinate shale. And at the upper part of the stream, we can find the sandstone with a weathering state at grade 1 to 2, and it is structurally jointed. For field investigation, we conduct the field investigation to find out the major and contributing factors which caused the debris flow event. And also during the investigation, we try to record all the accumulation zones, and we try to measure roughly the amount or the volume of the accumulation zone. And also we conduct a discontinuity survey at the expected source of failure, and we conduct a kinematic analysis. So the result, during the field investigation, we managed to find out the location of landslide. You can see the yellow point. That one is the landslide, and also we also mark all the accumulation zone, and also the erosion or scouring places. And this is the location of the landslide at the upstream area. The discontinuity plane is dipping outside the slope or the lighting and has a tendency to move in response of gravity. And we also find that the stream at the upper side of this Sungai Mandi river, it is very narrow and have a V-shaped stream, and it can cause the water clog by the accumulation of rock from the field slope. And we also find some of the scouring or erosion of riverbank, and it consists of colluvial deposits. And we also mark about 12 zones of accumulation. The zone of accumulation is marked as red dots. And this is some of the picture of this accumulation zone at the SEC2 and also SEC3. We try to measure the volume of this, roughly the volume of this accumulation zone, and we find out that there is 3 locations that have a huge amount of debris relatively, which is at the SEC2, SEC8, and also SEC11. And we also conduct a kinematic analysis. The discontinuity survey was conducted at the adjacent outcrop near to the landslide body, and there are 3 major joints and 1 bedding plane observed during the investigation. And what we can find from the kinematic analysis, the plane 4, which is the bedding plane of the Kayan sandstone, is possible to experience planar sliding. Plane 4 is the plane with red line, and there is no wedge failure is possible to occur at this area. And for the plane 1 and plane 3, they are likely to experience a toppling. And for discussion, we can see the planar failure obviously at the site, and the result of the kinematic analysis is tally with the type of failure observed at site. And there is a possibility of landslide recurrence at this area, where some parts of the overburden soils are still hanging and ready to fall. And there are 3 debris accumulation zones which are holding huge volume of boulders and trees And the most critical is the accumulation zone at SCC2, which is the largest and nearest location from the Damai Beach Resort and also Damai Central. And we also find out that the Kuching waterboard water tank beside the accumulation zone SCC2, and it needs to be secured from this flow threat. And during the event, the fencing was collapsed due to, that was disrupted by the flow event. And another thing I want to share is Sungai Mandi is among the major river at Santubong Peninsula, and it is located at the water catchment area and drain high volume of water from other tributaries river during the raining season. So it's quite huge water catchment area. So during the raining season, so the water will accumulate and flow into the Sungai Mandi. And this is some of the summary of this investigation. You can see the location of landslide, the location of accumulation zone with red dots, and also the scouring and erosion of riverbank. And this is the recent site condition. This picture was taken about 1 week ago, and even though it's not much changes, I think, at the site, but even though the situation seems like good, but we still need to take a precaution so that if anything happens, we are prepared for it. And some recommendations, the ground condition of Sungai Mandi provide a characteristic to become a debris flow potential area with a narrow V-shaped stream, the daylighting sandstone bedding, colluvial deposits of the riverbank, and also the big catchment area. So the local authorities must take an initiative to remind people for not having any activities at the Sungai Mandi, especially during and after rain, by putting a warning signs at the spotted location. And we need also have a periodic monitoring program. And we suggest that a detailed investigation to identify potential slope failure location that can contribute to the slow event is necessary. Maybe we can try to utilize LIDAR technology because this area is quite highly vegetated. So by using a LIDAR technology, we can get detailed information about the ground. So we can try to identify the location of possible landslide in this area. So as the conclusion, the landslide that happened at the upstream area of Sungai Mandi was the contributing factors, while the intense rainfall during the day was the triggering factors of the event. And the slope at the landslide area is possible to experience two types of failure, which are planar failure and also toppling. And the debris from landslide was probably forming a natural dam at the narrow stream, then later burst once exceed the limit and brought down the big volume of debris down to the coastal area. And the total estimation of accumulated debris along Sungai Mandi is about 21,000 cubic meter. And the large and nearest accumulation zone to the Damai Beach Resort and Damai Central is at the SCC2. I think that's all for me, Mr. Jetish. Thank you.
Thank you, Mr. Muhammad Farid, for the very interesting presentation. So I noticed that in your presentation, you were mentioning about the authorities has to be more notified. Were the authorities ever been notified about putting up a signboard such as the warning, especially during to be careful of the potential hazards?
Yeah, I think this was happened in 2015 actually. As far as I know, there is no action have been taken to take any precaution or mitigation measures after the this event. And what I see is just they try to repair back or mitigate, do some mitigation of the structure at the downstream of the area that caused a damage near to the Damai Central and also Damai Beach Resort. That's all I think.
Okay, thank you, Mr. Muhammad Farid. So I would like to open the question to the floor from right in our chat room. I think that there is no question on that. So I would like to thank Mr. Muhammad Farid for the presentation, and thank you for sharing with us the information. Thank you. Yeah. So for the closing of this track, this session, so we would like to invite the director of JMG Sarawak, Mr. Hilary Mulyan Nicholas Thomas, to share his views on this. Please, Mr. Hilary. Mr. Pangarah, Mr. Hilary, yeah. Yeah, we can see you now. We cannot hear you. Voice. We cannot hear you. Audio. Audio. Try on more again. No, cannot. No sound. no sound. No sound, no sound. Okay, we can hear some sound.
Hello, Mr. Jyotis.
Yeah, we can hear you loud and clear.
Can you, all right. Okay.
Okay, proceed, please.
Good afternoon, ladies and gentlemen. We are more or less at the end of this event, the 13th International Unimass Engineering Conference 2020 with theme of empowering the industry and transforming the society and engineering, science and technology. So first of all, I would like to thank you for our today's speaker from the morning session, that is Dr. Ray Rasme, who are talking about on the assessment of subsurface condition of peat soil due to the breakage, groundwater seepage, and then follow up by the engineer Dr. Nur Azalina Muhammad Sadon, talking on the peat settlement observation in Sri Aman, Sarawak, where Sri Aman is my hometown. But I don't know whether you still keep the name of Sri Aman, because they should change Sri Aman to Simangang. Yeah? So then followed by Dr. Raudah Ahmadi, talking on response spectra for moderate seismic area application to MIRI district of Sarawak. And then the afternoon from my colleague, Mr. Roslan Rajali, was talking on tube well construction, hydrogeological conceptual model and peat management to combat the prevalent peat fires at Kuala Baram, MIRI, Sarawak. Then followed by Mr. Edward Amor, talking on generating landslide susceptibility maps using airborne LIDAR derived parameters and geological mapping factors for Canada Hill in MIRI. And lastly is from Mr. Farid Abdul Kadir on debris flow study at Sungai Mandi, Sentubong, Kuching Division. So special thanks also to Mr. Jyotis John as a chairperson for the two-day conference, and not to forget Mr. Dr. Raudah as our moderator. And thank you for the others attending this conference. I don't know whether my friend in Semenanjung, Malaysia, Mr. Nizarul Ikram Abdul Rahim, the Director of Operation Implementation Coordination in our HQ, and Dr. Firdaus Ahmad from the Technical Services Division in Ipoh, who joined us, and few colleagues from NIMAS or other agencies. So, ladies and gentlemen, this event is very fruitful, as it provides the opportunity for INIMAS and JMG to share knowledge related on peat-related study and its environment and other related fields, such as groundwater and earthquake study. So I believe that we have the abilities and the expertise in this field to be developed further. So as we are all know now, the state government has formed the Sarawak Economic Action Council SEAC to facilitate the state government post-COVID-19 exit economic strategy up to 2030, where they review the development strategies under the 12 Malaysia Plan, that is by next year 2021. So based on our presentation today, I'm sure we can come up with the conclusion that maybe a benefit to the state, especially in the field of agriculture and other related sector. So I suggest we take this opportunity to assist the state government by supplying relevant data or information in this field. So another point is that I may suggest for the next conference, UNIMAS can extend your invitation to the other related state agency, such as soil units in the Sarawak Agriculture Department. So at least we can share some data, especially about the policy on the state side, because like JMG, we are on the federal side. So I think it's better for us, when we work together with the state, we have to know what is the policy on the other side, on the state side. So I think, so with that, once again, thank you, Alimas, for organizing this conference, and hopefully we will meet again next year with more papers will be presented, and stay safe and vigilant. Thank you.
Thank you, Mr. Pengarah, Mr. Hilary Moyan, for the closing remarks. And I'm sure we will look into that suggestion whereby we will get the state government involved in the coming conference. So, thank you. And now starts the end of the session. Goodbye.